Okay, let's start. Hi, everyone. Let's start. Okay. So, I sent a note on Piazza with a link to a web form for you to submit your project proposal by tomorrow, end of day. Basically, besides names of people in the team, you have to submit the URL for the GitHub repo. Those of you who have never used GitHub, it, you might want to familiarize yourself, but kind of the basic idea is that it provides a folder for your projects, and in which you can collaboratively share information. But a lesser known thing about GitHub is that in addition to storing software data, stuff like that, you can also add to each repository a corresponding website. And GitHub calls it as GitHub Pages. So actually, if you go to pages.github.com, you would see that. And essentially what happens is uh, it kind of describes, there's a little video and all, but the main thing is you want to select the one for project as opposed to personal. So it allows you to create a page for yourself. So your GitHub presence, a lot of people use that as their main website, but here you have to do it for a project. And then you can either use a template or start from scratch, but then it guides you. But the basic idea is, let's say your repo is called my project, then you have to create a top level index.html file, and you can either use some other HTML editor and copy from there, or if you are comfortable enough, just directly write to it. And then you have to create a branch under this thing, so it kind of guides you through it. You can follow that, but the main idea is that as part of the repo is also your project website. And at the end, what happens is that your repo is called whatever, github.com, your name followed by the repo name, but your website would have a URL which looks something like this: username.github.io/repository. So let's say, for example, my GitHub ID is M Srivastava. So anytime I create a repo with an associated website, then the website would have this top level link, and basically it kind of then picks up the file. So just follow the instructions. It's reasonably kind of straightforward. Just to show you what I'm expecting, so this is from one of the groups. So in essence, everything goes here. At the end of the quarter, I download the repo and everything should be in it, other than huge data files, which you can put into your UCLA box or Google Drive or something and include a link out there. On this website, think of it like right now, you just have to create a summary of the project, and that some project summary should basically describe what the goals are, what the approach is, and what are the envisioned milestones and rough timeline. Think of the timeline in terms of kind of a midterm goal and a final goal, final shape. Okay. So my Piazza post kind of describes those things. Also, it would be good to have a reference section, so see how these get a project abstract, materials and methods. That's basically your approach. Results obviously is going to be empty right now, and then references and stuff like that. Okay, they put some cute graphics and all, but that's not essential at this point. Objective, a stretch objective, you might want to think in terms of a baseline objective and something which is more aspirational, and then certain key references, at least to start with. The next milestone, which was originally due this Friday, but let's say we are going to stretch it out again a week from now, should have more detailed thing. By that time, you should have done your homework in terms of what are the issues. As I'm discussing projects with some of the teams, we are kind of encountering issues. Like, for example, those of you who are using the eSense hardware, it turns out it has microphone only on one of them. So sorry, it has microphones on both of them, but the software doesn't allow picking up data from both the microphones. So you're kind of running into these kind of issues that you only encounter as you start diving into the details. So those details and all sort of certain feasibility issues around hardware and all, that's kind of your responsibility, and this is what right now you should be digging into. Also, we have way too many projects on the eSense side, and half of the projects seem to be cloning each other. They're all kind of are about head orientation. So to make your project distinctive, you do need to think differently. So the only eSense based projects that I'm going to allow should have some distinctive flavor, okay, not kind of a me too of what already exists. But I've heard some pretty good ideas. Also, for a project to be approved, you have to either speak with the mentor or to me or both. By this time you should have done it. So if you haven't done it, there is a huge problem. So do it like today after the class. If you have a team of 3, then the project scope should justify a team of 3. So in some cases, I'm seeing just a team of 3 put together just because you feel like having a team of 3, and that's not reason enough. Then you have to expand the scope accordingly to justify a team of 3. So just my suggestion is a good team size is 2. 3 becomes too unwieldy. Oh, part of the other thing also I want you to describe in the submission to tomorrow is what will each individual do. This is partly to force you to think about like is what different expertise everyone is bringing and kind of scope it out. No point in having a team and then everyone is doing the same thing in parallel. Okay, to have a team work, best split the work so that different aspects are being chased by different individuals in the team. At the very end, I would ask each team member to write an independent thing as to what everyone did. This way I kind of squelch any complications about, oh, this teammate flaked out or stuff like that. So kind of just make sure everyone is carrying their weight. So you would see this one, this is by Swapnil out here. So you kind of see that there is this initial one, and then is your repo name?
Yeah.
.github.io?
Yeah.
Okay. Yeah, so I think it's just kind of confusing, but like your repo name typically would probably be just a single phrase or something. Okay. So anyway, if you have any troubles with any of these aspects, just talk to me. Or I guess the other thing also is these guys used Weebly, which is a nice online tool to let you create websites, and you can export HTML output from that and then put it anywhere else. Okay, but there are plenty of other ways of doing it, but not every tool lets you do it. Like for example, if you are using Google Sites, then Google Sites does not let you export the HTML, okay, because internally I don't know what they use. So Google Sites is probably not a good choice, but there are plenty of other tools which let you create HTML websites and dump the HTML, and then you can just import it into the GitHub thing. Okay, so hopefully this is not too onerous. Again, right now you just need to get the structure in place, and the initial stuff is, think of it like just those sections kind of corresponds to roughly no more than a page worth of material at the stage, basically. And the only other thing is that only one person in the team should submit that. Okay, so I don't want multiple submissions. Okay, and there should be only one repo owned by one person. And final bit, ideally I would prefer if you're okay with making your project repo public, but let's say you are not for whatever reason, that's your right, in which case you should share with me on my GitHub ID. Okay, and I'm fine either way. You're not going to be penalized either way, but I think it sort of is good if within the class at least we can share. So any questions on what's due tomorrow? Okay, great. So moving on then, last time around I had started on timing related considerations, and in particular, so one point I'd made basically was that how failure to kind of meet deadlines and all have historically been kind of at heart of some of the well-advertised failures. And then towards the very end, I was talking about different type of timing constraints that exist. And very broadly, you have timing constraints on the system in terms of its performance, and there are timing constraints on the environment, or another way of timing expectation. So you can think of almost like a contract that exists between the system you're designing and the outside world, and oftentimes the outside world is relatively brittle. So unlike human behavior, where if the computer is slow, we kind of wait. When you have more physical systems and all, they are more intolerant. So essentially, failure to meet deadline means your system really isn't working. So system is incorrect. The other dimension we had talked about was that how constraints fall into maximum constraint, minimum constraint, and kind of durational constraints. And with that, for maximum timing constraints, I've shown examples where the constraint exists between successive or two inputs into the system. So this is really is a constraint on the environment as opposed to the system. So the expectation on the environment, and essentially the idea is if the environment doesn't behave according to this, then the system may not operate correctly or even maybe unsafe, but that's okay because it's not a violation of the contract. So one has to be careful about making sure that you understand what the environment is behaving like. Then you have constraints on the system, in this case input to output, stimulus to response, and this is saying something about the speed of the system or ability to meet a deadline. From the point, a stimulus which you can think of as an interrupt coming in, which perhaps results in a task getting triggered, task moving from waiting to ready, and then response is when the task reaches a certain state, like for example it finishes. So it's saying something about the speed of the system, and that requisite speed could partly come from having a good algorithm, a fast algorithm, fast data structures, and also can come from having hardware which is speedy enough. Response to stimulus is after the system has done its output, when the next stimulus comes in, and again this is saying something about the speed of the environment. And then finally response, and this corresponds to two successive outputs from the system. So oftentimes the system has to sequence things correctly in the environment, apply output in a particular sequence and all. Minimum follows the same sort of flavor except in the reverse direction. So for example, SS combination, a minimum time between two inputs from the outside. And this in a way is saying that this is covering the, this is again sort of, while it's a constraint on the environment, it really is because of the speed limitations of the system, because after taking one input, maybe you won't be, the hardware is not fast enough to handle the next input. So this is really saying that if the next input arrives too quickly, then the system may fail. Minimum SR, a minimum time is required between stimulus and a system's response. This is partly, this is really saying the system should not be too rapid, because sometimes if a system is too quick, then the outside world is still kind of recovering and is unable to ingest the next output. So this is often the case when the outside world is, let's say, a human or something, right? Too rapid, you might miss it. Response to stimulus, so minimum time between the response and the next stimulus from the environment. And then finally RR. So kind of they correspond to obvious interpretations. And then even these constraints are often too simplistic. A lot of times we have a lot more complicated scenarios where essentially multiple events could be stitched together and they should satisfy some constraint. So There are more formal ways of dealing with these things. There are formal ways of expressing timing requirements. Usually, as electrical engineers, we first encounter these things if you ever do digital hardware. So usually chips come with timing diagrams for their interface attached to them. And when you're designing, like interfacing a memory chip to a microprocessor chip, you have to make sure that all the timing requirements are satisfied, like read-write signals to the memory or a I/O chip and all. But kind of the same thing holds true at any interface, that there is an associated timing requirement. Now, this is an issue not simply at the hardware level, but also at the software level. Now, usually, when it comes to the type of programming that we do, generally the timing constraints are kind of buried. They're implied, and they're typically implied in the logic of the program. So your languages like C or C++, they don't have any notion of time built in. So what happens is that the operating system provides you some additional functions using which you bury time into there. So like, for example, let's say you have to do some output and then you have to wait a certain minimum amount of time before doing the next output. Then in Unix, for example, there's a function called sleep, or there are variants of it. So you will do that output, sleep for a certain time, then do the next output. Except sleep is not a language characteristic. It is provided by the OS. So if you're running on Windows, it may have some different call. If you're doing on a different language, maybe it will expose it differently. So what happens is that usually providing support for meeting timing constraints in software often is kind of this appears in the form of these calls, API calls that the OS provides. But in many cases, there also could be part of the language itself. So there are languages which have support for timing built in. And you particularly see them for languages which are meant for targeting hardware design. So those of you who have done Verilog or VHDL based VLSI design, or if you might be seeing it in 216A, for example, these are languages which have timing constructs built into the language, because the idea is that those timing constructs have to be honored by whatever software then eventually generates the hardware. But on software side, it's usually less the case that timing is built into language, but usually timing comes from the operating system. So kind of things you would see are kind of things that, by the way, this should not say loss, it should say OSs, operating systems. Let me kind of fix it right now. Okay, so kind of things that you would want to be able to do in software. Measure elapsed time. So you did something, and then before you do some next thing, you want to make sure that how much time elapsed. Very trivially, we encounter them if you want to simply measure how much time your code took, for example. But you might also need to do it to, say, generate some sort of waveform or something. Another thing that we encounter is by delaying a process by certain time. So I did something, and then I want to wait for a certain time. So for doing something like this, where you measure the elapsed time, usually there will be some provision for having some sort of a timer, and you are going to read the current time, start the timer, stop the timer, and read what happened. That's one way. Another way, you read the time here, subtract the two. So a variety of ways you could kind of do it depending upon how you're measuring things. So let's say there's a piece of code whose runtime you wish to measure. So a very common thing that we often have to do is that we would like to measure it over multiple runs, multiple iterations. So you can have a timer, start, stop, restart, stop, so on and so forth. If you're doing just one shot, then just reading the time and reading the time here. It used to be that these timing capabilities were pretty coarse, but nowadays in Linux, for example, there are timers which go to essentially clock cycle precision, so you can measure things down to orders of tens of nanoseconds or certainly sub-microsecond. One other thing to be careful about is that most of these operating systems, like if you read time in Linux, then it returns a time data structure, and there it has two fields, and one of them is in nanosecond, but that doesn't mean that all those nanosecond bits right down to single digit are valid. Fundamentally, you are limited by the accuracy of the underlying system clock. So if it can only measure things to, let's say, a microsecond, then the lower digits in nanosecond are going to be basically pointless. So one has to be careful that when you're reading these timer values, not all bits are valid. A lot of them, the lower bits might basically just be noise. For delaying a process, usually you'll have something like a wait or a sleep or something like that. And what happens here is when the application calls that function, then this is an example where the task is no longer able to run. It is waiting for a resource, except the resource in this case happens to be time, the clock reaching a certain time. So at this point, when the wait or sleep is called, then the task is put onto waiting state, and some other task takes over. So that's an example. Timeout. So timeout refers to this notion that I'm doing something, but I want to make sure that if doing that something takes more than a certain time, then I want to exit doing it. So a typical example for this is if I'm trying to do some I/O. So I would say wait for that data to arrive, but I don't want to wait for more than a certain time because maybe the outside world is hung and I want to take some corrective action. So that's the timeout thing. So how would you do timeout in, let's say you are writing code in C or your favorite programming language? Like how would you go around doing timeout in some language? So again, I'm doing something, but I'm trying to guard against getting hung in doing something. So I want to make sure that somehow I can get out of that.
You told like calling that event.
Yeah, but how would I get back? So I can certainly call that event, but if I am doing, let's say by mistake, somewhere in that code I have forever loop. Okay, so the code is just hung doing it. Okay, so I'll never get out of it. Or maybe I made a read to a hardware device, and that hardware device is just not providing the next sample, and I'm kind of hung doing that. So how can I get out of it?
Have a counter in the loop. And
well, I mean, you are literally hung, right? I mean, there is you can't. So one way is to use threads. You have this thread which is potentially can hang, and then you have a separate thread which is what is going to use one of those. Let's say you could use delaying function in that other thread, and when that thread reaches that, it can check whether the thread which can potentially hang is problematic or not. Okay, so you could use some combination like that. Sometimes functions provide a timeout capability. So like in Unix, there are read and write calls to devices where you can specify a timeout. So you could basically say, read from this port, but if you don't get the data within 1 second, then just return. Okay, and then you can check the status whether you timed out or not. So sometimes operating systems will provide you calls with timeout capability built in, or sometimes you can fake it using these threads. In C, what you could do is there is a concept of, or in really Unix, there's a concept of signals, and you can arrange for a signal to be delivered when a timer event happens, and then you kind of build things. So there are ways of doing it. Finally, deadlines. And the idea in deadlines is that you want to execute something and you want to make sure that it finishes by a certain time. So this is where you do need the cooperation of the operating system, because operating system decides whether you actually get to run on the CPU or not. Recall that diagram I had where the task could be in different states. So you want to make sure that the operating system is moving things to the run state, executable state, taking into account these deadlines. So for example, if some task has an early deadline, then maybe it should get more priority to run on the CPU than a task which doesn't. So deadline will have to be some sort of indication from the application to the operating system exhibiting its needs. So for example, the stimulus response type constraints could be realized using a deadline. So when interrupt comes, you spin off a task and you can tell the OS, make sure you finish it within so much time. And of course, needless to say, execution time of that task should be less than the time to the deadline, but beyond that, the operating system gets some slack on when to run things. So much of what I'm going to talk about now is really going to focus on this last part, deadline. The elapsed time, delaying processes, and timeouts, these are all about handling timers and all, but deadlines are foremost about scheduling the thing. But there are all sort of other, all these other things also involve cooperation of OS and the underlying
I'm really
hardware.
sorry, someone left an adapter in here that I need for a training class right now. Do you mind if I
Please.
take a quick look?
Sure.
Okay,
Go ahead.
sorry about that. It looks like,
I didn't see anything, but
I know, I didn't. It doesn't look like it's here. Alright, I'm sorry about that.
sure, no problems.
Thank you.
Okay, so again, remember I talked about that how these timing requirements and these things are kind of like a contract. In our case now, they're a contract between the application and the operating system or the underlying runtime. Very simple way these. So over whatever past 20, 30 years, many different models have emerged for expressing these timing constraints and stuff like that. But a very common scenario that we encounter where timing tends to be important are settings where we are processing some sort of a streaming data, sensors data coming in, network packets coming in. And usually these are things where, or not always, but often these are things where you are just operating forever. One batch of sensor data comes in, you process it, next one comes in, you process it, and you keep doing it. And so a very common model is that I have a task which is repeatedly being invoked whenever the next batch of data arrives. So motivated by this, a very common model then is I have a bunch of independent tasks. These could correspond to, for example, different sensors and actuators and whatnot. And each one of these tasks have a period associated with it, which indicates the arrival rate. So like, for example, I may have a audio task which is kicking in every time a batch of audio samples arrive, and that's designed to be some sort of periodic thing. Much of signal processing in electrical engineering has always taken place with uniform rate sampling, so periodicity kind of fits in nicely. So there is a rate for every task which is defined by that period, and you can think of it as next batch of data coming in and you are processing it. But this is not the only model. There are also systems where things are very asynchronous. Like, for example, let's say you're designing a air traffic control system, and every time a plane comes in, that task has to handle it within a certain time. So in that case, things are very asynchronous because arrival of the planes are certainly not periodic. One of the ways to handle that is that you can think of those aperiodic tasks, those asynchronous tasks, as having some sort of a worst case period that you are working with. But anyway, right now we are going to stick with these this model of everything is periodic, but potentially with a different period. And another thing is that life would be pretty simple if I knew for each one of these tasks when the first request came, right? Because if I knew for each task the period and when the first instance came, then effectively I know forever when the different instances of a task arrive, and then I can just solve the problem statically, right? So for example, if I could say the first copy of task 1 arrived whatever, let's say at t equal to 1 and its period is 5, then I know it comes at 1, 6, 11, so on and so forth. So if I also knew the time of the first request, which we are going to call as phase, R1, R2 through Rn, if I know that, then I have a static problem at hand, and I can, before even running the system, I can check whether all the deadlines are going to be met or not. But the more general case is that my system starts up and is now ready to handle these incoming tasks, and I have no idea when the first tasks would arrive. So these are unknown also, and so I have to design the system so that for any arbitrary value of Ri's, I can still assure that the system would work successfully. Also, of course, the problem would be trivial if I didn't have to worry about execution time. So all of these tasks, there is also a notion of the runtime that exists. So every time the task, a request arrives for task I, let's say for task 1, a request comes. So requests are coming every time T1. The first request came at time R1, and the request takes some time C1. Okay, so this is the actual computation time. Now, the problem that we face is that when you have to do some processing, we usually don't know how much time it will take because it may depend upon the data. Like for example, it could depend on the value of the data because there may be some for loop in there, okay, and maybe that will, so there are many iterative algorithms and they may depend upon the actual value of the data. So until you see that value of the data, you have no idea how much time that request will take. So what we do out here is, because remember we are worried about making sure we meet the deadlines, so these things correspond to worst case execution time. So we basically somehow, let's say, magically know what the worst case execution time is. We do something very similar in hardware also. When we decide the clock period for a hardware, then we compute it based upon the critical path through my logic. You look at all the input output delays under all possible transitions from 0 to 1 or 1 to 0, and we kind of compute which is the worst case path through the combination logic. It's the same thing in software, that irrespective of the values of the data and all, you want to compute the worst case time. In many processors, even instruction times can depend upon the value. Like for example, if you multiply with 0, maybe the multiplier would be quicker than not. So any instructions which are multi-cycle instructions can potentially take variable amount of time. There are some papers which show that if you look at kind of processing we do in signal processing and all, the variation between the best case runtime and the worst case execution time could be pretty huge, orders of magnitude. So for example, take JPEG images, compression. When the image is kind of very simple, flat white, flat black or something, the compression is very quick. If on the other hand the image is very complicated, a lot of texture and all, it takes more time. So variation in a lot of these algorithms is actually quite significant. How can you compute execution time? If I give you a piece of code, and let's keep life simple, it starts at the top, ends at the bottom. Okay, how would you go around computing the corresponding C? Like how do you how do you like? Huh?
There are functions in MATLAB to do that.
I don't. What do you mean functions in MATLAB? I don't think MATLAB can do this at all.
Yeah, we use like a function called TikTok to do that.
TikTok.
No, but that only tells you for MATLAB. It's not telling you for running code on a processor. And how would you get the worst case? That's the other part.
Maybe run through the all possible inputs.
Okay, so you could run through all possible inputs. So let's say you want to do it for JPEG images. So what will you do? Run through all images?
No,
No, right? Okay. So what do we as engineers do when faced with this kind of thing? What are one approach is we do Monte Carlo simulation. So we do some random sampling of the input space, look at the distribution, hopefully we capture it. Now the problem is input space is huge, so you may very well miss, so you add some fudge margin to it. So that's one approach. Okay, what do we do in hardware? Again, taking that analogy, you know the delays of primitive elements like gates, and then you try to find mathematically through graph algorithms the worst case path through your circuit. So you can do the same thing in software. You can basically have algorithms which trace to the code and try to find what is the worst case scenario going to be. So you formally try to come up with the runtime for these codes. So there are runtime estimators which can walk through the code, essentially unroll the for loops and all to find the worst case path. Do you see a problem? So in case of hardware, it works reasonably well. I'll give you a circuit with AND gates, NAND gates and all. You kind of find the worst case delay path through it. Even there you have problems like there's dependence on temperature, and the delay from if my input is 0 or 1 may differ. But let's stick with software running on a processor. Do you see problems in what kind of problems can make computing execution time hard?
different processes will take different time.
Why?
Maybe the programming problem. Maybe programming part.
Let's say I give you a piece of code to run on a processor. It's a very simple code, bunch of instructions with no fault, nothing, no branching, just a set of code operating on a piece of data. Is there something about the processor which can affect how much time running that piece of code might take?
Does it depend on the time complexity?
No, it's a set of instructions. As you know this piece of code. I mean, you're given it. So what I'm trying to arrive at is that is there an uncertainty in that execution time? I run it once, it will give me some time. I run it the next time, it will give me a different time. Do you think something about the processor affects the runtime of code? Caching. Yeah, branch prediction can also affect things. You're absolutely right. So caching, so let's just walk over it. Caching affects it because if my data are already in the cache, then the code will run faster versus if it has to fetch it from outside. And branch prediction affects it because if the branch prediction predictor was right in taking the right branch, then it would be faster. So point I guess I'm trying to make out here is that even something as simple as what are these C's depend upon a lot of things. So worst case would be you flush the cache so that you don't make any assumptions about the data being there. And I guess if you have a branch predictor, then you hope that the branch predictor was trained incorrectly so that you pick the worst case. So getting the worst case execution time itself can be pretty challenging. Okay, then finally deadline. Now if you have a single processor and it is operating on a stream of samples coming in, gets one sample, processes it, gets another sample, processes it, and so on and so forth. For this whole thing to make sense, it stands to reason that the deadline should be equal to the period, right? Because if the deadline is, deadline should be no more than the period. Because if deadline is more than the period, then I will back up, right? I mean, I cannot keep up with the data rate. So, so the deadline for me to handle an incoming sample is before the next sample arrives. And so a very common model is to just set the deadline to be equal to that period. Okay, so this works very well for signal processing kind of things, because you have a stream of samples coming in, one sample, process it before the next one comes in and all. Now, strictly speaking, this is only an average requirement, right? I mean, what I want to make sure is that I don't fall consistently behind. Okay, so if I have some sort of a queue in which these samples are coming in and the processor is processing them, then strictly speaking, I would be fine if that queue never overflowed. But a simple way of dealing with this thing is simply saying that I always keep up. One sample comes before the next one, I'm done with it. Now, this is a purely hardware-oriented requirement. Let's say I had two processors. So one sample comes in, I process it. The second sample comes in, I can farm it out to the other processor, assuming there was no dependence between the two, and I would be fine doing this. In which, so the real limitation, there is a separate limitation on deadline which comes from the humans, as in, or whatever, the consumer. So, like for example, I don't want the video coming in or audio coming in to be delayed a lot. So if I'm engaged in a bidirectional conversation with you, then if audio and video from your end coming to me is delayed significantly, then bidirectional communication becomes a problem, because you'll speak something and then when I hear it, I speak, and meanwhile you thought I'm not speaking, and then you'll overspeak, right? I mean, we kind of run into these issues. A lot of psychological studies show and all that for round-trip conversation to be meaningful, particularly audio, we should be around 150, 200 millisecond. Any round-trip delay more than that begin to lead to significant impairment issues. So there are two so this constraint, d equal to t, is kind of really a local artificial constraint, because it doesn't make any sense for that deadline to be any more at that processor. But when I'm looking at an end-to-end system like that, bidirectional, let's say Zoom or one of these, Skype or something like that, then the end-to-end constraint is really for each one of these stages, right? So one of the challenges nowadays is that things like cellular system have a lot of delay budget. If you go through cellular system and all, right there, you probably eat up 100 millisecond or tens of millisecond of delay right there, and a lot of them comes from the type of compression algorithms and all they use. So in an application, you really care about end-to-end delay, but locally on task running on a single processor, this stands to reason. So deadline equal to period, or you might pick deadline less than period also if you care about end-to-end delay. So like for example, let's say whatever task I was running on this processor was a part of some bigger end-to-end system. So I may not be happy with saying deadline equal to period, because then my end-to-end delay can suffer. But again, for now, we can say deadline equal to period, because these periods for sensors and all tend to be pretty tiny anyway. So the delay that being added is not that much. So our model now is bunch of tasks with a period, so that a new copy of that task is started every period. We want to make sure a copy finishes before the next copy of that task I, is started. We'll assume that we know the worst case execution time. So clearly it stands to reason that the worst case execution time Ci would be less than the period T sub I, because otherwise we can't meet the deadline. And that we don't know when the first task arrives, so that we can't solve this problem statically. And so now with a model like this, how do we go around? How do they get implemented? So firstly, there are lots of kind of typical assumptions or typical settings that work. So single processor, everything is running on a single CPU. These things are mapped into separate threads, separate we kind of saw these things last time. So let's imagine that each thing is running as a separate process. All the lower level details are kind of taken care of by the OS. And all we are worried now is going to be how can I run these different instances at any given point in time. There might be multiple different tasks which may be ready to run. How can I run them so that all my deadlines are met? And that is the job of the scheduling algorithm. So scheduling algorithm basically shuffles tasks from between the ready to run queue and the actually executing queue. Okay, so again, recall that diagram. Waiting, I can't do anything about the task. If a task is waiting, then it has to keep waiting until the resource is ready. We'll see one complexity out there for the moment. But so really what we are worried about is which task gets to actually run on the CPU among those which are ready to run. Now, a complexity which comes up out here is the following. Sometimes if the tasks are not independent, if one task produces data that another task may need, then I may have to, even if the task producing the data is not a very high priority one, but the task which needs the data is the high priority one, I may still need to run the first task so that the high priority one is not waiting. So there are complexities like that, but that's the main. So one very common approach to do all of these things is what is called as preemptive priority-driven scheduling. So preemptive, I talked in one of the previous lectures, is this notion that the operating system can stop a currently running task and give the CPU to some other task. It's not simply about CPU and things. You can think of the same thing on a communication channel, that I can stop the current communication and start communication for something else, some high. Okay. And so preemptive basically means that we can stop in the middle to give to someone else. Priority driven basically is the notion that we are going to think of different tasks which are competing for the same resource as having a priority. And we are going to follow a very simple policy that at any given point in time, the task which will actually have the hardware and run on it is the one which has the highest priority. So that makes the job very simple. At any given point in time, we see whichever is the highest priority, we give the resource to that. Something may cause this priority to change. So what might cause that priority, the highest priority to change is, for example, let's say a new data sample comes from outside. A new audio sample comes in, and now the task which was going to process it is ready to run. And if this task has the higher priority than the currently running one, then I'm going to give the CPU to that. Another one is one task generates or does something. Like, for example, it stops using the radio. Let's say there was a task which was using the radio, and now it stops using the radio. The moment it stops using the radio, it could be that some other task which was waiting for the radio now gets ready, and if it is higher priority, then it gets to run. So there are all these actions in the system which may cause some other task to become higher priority, and all our policy is that at any given point in time, I'm going to make sure that the higher priority task is the one who gets the hardware resource. There are couple of special scenarios, versions of these things. So one is, we can say, I'm going to assign priorities statically. So up front, when I know what the tasks are, compile time, I'm going to give them priorities, and they are fixed forever. And the other one is that I let the priorities change at runtime. Okay, so something would cause the priority of a task to change, and if the priority of the task rises or falls, that is going to affect my decision on which one is running. And sometimes you may have mixed. Some tasks may have a fixed high priority, and some tasks may have dynamic. So one way of thinking about hardware interrupts is that hardware interrupt is a highest priority task and is fixed to be highest priority, right, at the hardware level. It will always, unless you disable the interrupts, it will always interrupt anything that is running. So static versus dynamic priority, but our policy is very simple. All the OS is continually doing is the highest priority task gets to run. There is one common variant to this thing, which is instead of saying at any time the highest priority task runs, we can back off and say we will wait until the currently running task gives up the CPU. So we are not going to actually stop it in the middle, but whenever the currently running task starts waiting for something, and I have an opportunity to now decide which task to run next, I'm going to again pick the highest priority one. So bottom line is that ideally our goal is at any given point in time, the highest priority task runs. And most embedded operating systems, real-time operating systems, follow this policy. This is not the case with, let's say, your Linux or OS X or Windows, because they do not use this notion of preemptive priority driven. So in Linux and these kind of things, the goal is different. The goal here is to maximize utilization of the processor, and the other thing is to kind of keep interactive workloads happy. So what happens in these operating systems is that they look at what fraction of the CPU a task is using, and they take that into account. So they kind of are trying to be more fair. So if one task is using a lot of CPU, then they lower its priority conceptually and then start giving the CPU to someone else. You can forcibly change relative priorities that are given. There is a command in Unix called nice. So you can let's say you are running some heavy, I don't know, machine learning workload, and it's affecting the graphics, the interactive performance in your machine. Then you can nice that task, which basically means run nicely, as in run at a lower level of priority, and then it gets less fraction of the CPU. But that's very different in what's happening out here, that we have these priorities, and we'll see shortly that how these things end up playing a role in meeting the deadlines. But if all operating systems are following this policy, then basically really our ability to meet deadlines and all depend upon how we assign the priority. Which task should have higher priority, which task should have lower priority. Now, and because everything else is the same, right? I mean, if always I'm just running the highest priority task to the first order, then the only thing that comes in play that I have control over is how to assign the priorities. And again, very commonly static priority. Dynamic priority is much rarer. So most operating systems you'll find basically let you, at the time you create the task, you can basically say this is the priority. So your system would have a bunch of tasks, and each task is periodic, and there's a priority associated with that. Okay, so this picture we have seen earlier. So ready, waiting, running, inactive, and in a sense, whenever I have to move something from a ready to a running state, is when we are going to say take the one which is the highest priority. So highest priority ready to run task is task instance is the one which actually gets to run on the CPU. And again, I emphasize enough, even though I'm talking about CPU, the same thing applies to any hardware resource. Okay, communication channels are exactly the same way. So yeah, I mean, all these OSs which are used would have some support for it. So now just to motivate that this choice matters. So one way one would go around, like when you think of the word priority, the first thing which at least strikes to me is importance. I'm going to give more priority to whatever my programs and your programs. Okay, or I hope so, that's what happens. But point is, you could think of priority as importance. But that's not necessarily the right way of thinking about it. Just because at least not for meeting deadlines, right? Because for example, it could be that while it's important because it's coming from a more privileged user, but maybe that task has timing behavior which is going to hurt everyone. Okay, so that's not what we necessarily want, and we'll see that that's indeed the case. So let's take an example. Let's say I have a couple of tasks, task 1, task 2. Task 1 has a period of 50 milliseconds, task 2 has a period of 100 milliseconds. Task 1 has an execution time of 25 milliseconds, and task 2 has an execution time of 40 milliseconds. So basically, task 1 is coming every 50 milliseconds, and every time it comes, it needs CPU time of 25 milliseconds. So which means it needs 50% of the CPU. Task 2 comes every 100 milliseconds, and it needs 40 milliseconds, so it needs 40% of the CPU. So one very common mistake one might make is you'll say, okay, so one task needs 50% of the CPU, the other task needs 40% of the CPU, 50 plus 40, 90, so I need less than 100% of the CPU, everything is fine. But that's not true if you are worried about deadline. This would be true if I didn't care about meeting the deadlines. If all I cared about was that nothing backed up, right? On an average, I'm meeting things, but not if I'm worried about the deadlines. Okay, so looking at this utilization is not the complete story. Certainly, the 50% plus 40%, if it was more than 100%, then I would have a trouble. I would have a problem, right? So the utilization of the tasks necessarily cannot be more than 100%. If they are more than 100%, then what are your choices? Use a faster CPU, or what else can you do? I mean, if your code is too slow, what do you do? Run and buy a faster computer if you're lazy, or if you're what's your other alternative? Rewrite the code, use a better algorithm, better data structure, right? I mean, so that's the other option. So you'll have to do one of those things. Okay. So you do have control over C in a way, right? By either rewriting the code or by getting a faster hardware. To do that. Okay, so now what happens? So in this particular case, let's take, so I have two tasks. So really if I have to assign priority, I only have two choices. I either give task 1 high priority, or I give task 2 high priority. So what would happen? So in this case, what you're seeing is, so yellow is task 1, blue is task 2. So let's say I give task 1 high priority, okay? And let's say I start at t equal to 0, and let's assume that a copy of each one of the tasks has arrived. But since task 1 is high priority, it gets to run. So it will run for 25 milliseconds because its C was 25. And then the blue will start running, and blue, remember, needs 40 milliseconds, and it comes every 100 milliseconds. So it will start running, but at t equal to 50, another copy of task 1 would arrive because it's coming with a period of 50 milliseconds. So at this stage, the blue task 2 will get preempted, and I will again start from task 1, and it will continue to run until 75. And then the blue task will run, and since it had already run for 25, so it only will run for 15 more. So it will finish at t equal to 90. So it has met both tasks are meeting the deadline. Okay, and then kind of the whole process will repeat when again task 1 arrives at t equal to 100. But let's imagine we do it the other way. We give task 2 the high priority. So now at t equal to 0, the blue task will get the CPU. It will run until time 40, and then the yellow task will start running, and it obviously won't finish by 50. So we have a deadline miss. So the simple example shows that the deadline, the priority choices clearly matter. And the other thing hopefully follows is this has nothing to do with importance, right? This is entirely about the temporal, the timing behavior that is at play out here. Okay, so what this leads to is this area where, like, how can we say that can I schedule it, and if I can schedule it, how do I provide the priorities? So one thing which follows is that if you want to reason about this thing, then there is only one situation you really need to reason about, which is when a copy of all the tasks arrive. So let's say let's back up. So firstly, what we want to make sure is that no task ever misses a deadline. And the second thing is, what this theorem is really saying is that if I'm considering, let's say, a particular task number I, then the only situation I have to worry about is that a copy of this task arrives at the same time as a copy of every higher priority task in the system. So let's say I have task 1 to task tau 1 through tau n, okay, tau 10, 10 tasks. And let's say I gave them that priority. Task 1 is the highest priority, task 10 is the lowest priority, and in that order. And let's say I'm worried about, will task 4, a copy of task 4, arbitrary instant of task 4 will meet its deadline or not. So intuitively, stands to reason, and you can kind of prove it more formally, that the only case I have to worry about is when a copy of task 4 arrives at the same time as a copy of task 1, 2, and 3, which are higher priority. And the reason is, intuitively, I don't have to worry about 5 through 10 because they are lower priority. So they will never get the CPU in preference over that copy of task 4. And what's happening is, since 1, 2, and 3 are higher priority, they will grab the CPU and task 4 have to wait for it. And in fact, they may grab the CPU multiple times if the period is high enough. So this notion is called critical instant. So essentially, our job is to make sure that the response time of any task is less than its deadline. Okay. And the second thing is, I only have to worry about this critical instant where the copy arrives at the same time as every higher priority one, so that your waiting time is maximized. And if I can analyze this case and show that the deadline is not missed, I am good to go. So this is again kind of another 2 task simple example, that task 1, task 2, period of 2 and 5, and each one of them has a computation time of 1. What is in one case, I'm giving task 1 the higher priority, so it gets to run first. And if you notice out here that I have 1 unit of unused CPU time if I would run, but I could have even made C2 equal to 2, and I would still have been okay in this particular example. What it also shows is that if I were to swap the thing, if I give task 2 the higher priority, task 2 runs first, task 1 runs first, and in this particular case, I have no slack in the system. If task 2 took even a teeny bit more than 1, then task 1 would have missed its deadline. So again, this scenario where task 1 had the higher priority, task 2 had the lower priority, both are meeting their deadlines, but not just that, I have a little bit of slack in the system because I have this open time, because task 2 only needs to finish at time 5. So I could make use of this slack to slow down the CPU. I could have gotten away with a slower CPU and still be okay because I have some slack in the system. Whereas if I were to do it the other way, then I'm just barely meeting the deadlines. Task 1 and task because task 1 finishes at time 2, just barely in time. So if CPU was even a teeny bit slower, this would fail.
Does the processor have any idea on what the estimated or actual runtime is going to be prior to this? Like, do we send any information to it, or is
no? The hardware is totally unaware of
so
it.
this stuff is all
This is all the operating system is doing it. Yeah. So hardware is entirely agnostic to it, but operating system can do things like, which in this model we are not talking about, it can speed up the processor. Remember we talked about when we were talking about power that you can have frequency voltage manipulation done. So you could imagine that the processor under the control of the OS could speed itself up when something more critical is happening. Okay, and that's certainly a possibility, and in fact more advanced algorithms do that. Okay, but again, it's not that the hardware is learning that on its own. It's the OS which is kind of doing that. So the message, I guess, takeaway from here is that, oh, sorry.
In the previous slide, you were saying C2 is C2 like maybe more than 1 second, and you can just like divide it into like smaller pieces and then
Right.
have it run. Would it cause any issue like when you have a task running in like separate portions?
No, so remember, you are not dividing it. It's the OS. So let's say C2 was indeed 2 time units, right? So C2 starts running, and at this point, the operating system will just stop it, okay? And when it stops it, it has to save its state, and then when it restarts it, it has to reinitialize the state. So to the first order, it doesn't create any problem. I say to the first order because I just told you it saves the state and restores it, which does take some time. So this transition when a task is stopped, just to hand the CPU to another one, is called context switch. Okay, the CPU is changing its context, and there is some overhead associated with it. In these theoretical models, to the first order, we assume that it's much tinier than the rest, so you can think of it as a bit of a noise. But there are ways you could kind of factor that in also. There is hardware support for minimizing this transition. So for example, on some CPUs, what they do is they have multiple banks of registers. And so like, let's say they have 16 registers in the CPU, they will have maybe several banks of 16 registers. So when you move from one task to another, you don't even have to save those registers. You just start using a different bank. So there are situations where hardware assists in this process, but again, at the level of this analysis, you can say that time is very tiny, and therefore we are ignoring it. In reality, that context switch typically would involve saving, let's say, order of 20, 30 registers, so that many clock cycles. So what this means is that if I'm dealing with deadlines of like, let's say, milliseconds or 10 to 100 microsecond, and since saving registers and all are at the level of nanoseconds in a gigahertz processor, you are dealing with kind of errors which are like less than a percentage. So
In terms of like interfering with the whole task processing, it doesn't cause any problem, right? It's just like
no, it doesn't. In fact, you have remember the only contract that exists between task 2 and the operating system is that it must finish by time 5. That's it, right? So we don't care about intermediate things. So it's not as if the task doesn't have to run continuously. If there was some intermediate goal also, that the task must reach this point by a certain deadline, and then if there are multiple such deadlines, then you'll have to specify those. Okay, so in this case, all we are saying is there's a single deadline at the very end, and task should reach that at t equal to 5. Okay, so takeaway in this one is that the order in which we assign priority matters. And one thing you would see is that in both these examples, the one which I had here and the one which I had earlier, it's the task which has the lower period, giving it the higher priority is better. Okay, in one case here, remember in this particular case, when I gave task 1 the higher priority, we were able to run it. When I gave task 2 the higher priority, we failed. And again, task 1 has the lower period, 50 milliseconds versus 100 milliseconds. And something similar is happening out here also, that when I gave task 1 the higher priority, then I had a better schedule. I had a more relaxed schedule. I could slow down the CPU, whereas not in the other case.
These scheduling algorithms assume that tasks are independent.
Yes, we are going to visit when they interact later. So they are totally independent. Okay, so just imagine that I have a bunch of different things processing independent streams of sensor data or whatever. So
And they cannot use the same resources.
they are not even using the same resources. And again, we are going to visit how to incorporate that later. Yeah, good question. Okay, so that basically leads to the key result. which is that the optimum priority assignment is what is called as rate monotonic, which basically says that you should assign priority in order of the rate. Higher the rate of the task, you give it more priority. And moreover, there is a theorem which basically says that across all possible ways of assigning fixed priorities, this is the best you could do. Or put another way, that if I give you a set of tasks and I tell you you have to assign priority statically, no runtime game manipulation of priority, then all you have to do is assign it rate monotonic priority, that is give highest priority to lowest T, and check whether you still meet all the deadlines. If you don't meet the deadlines with the assignment, that means just give up. There's nothing else possible. If you do meet the deadlines, then this way, then it may be possible that there are other ways of assigning priority which will also meet the deadlines, but at least you have one. Now, some of those other ways may be superior in other regards, like maybe they might have better memory behavior, consume lower power, stuff like that. But at least this gives you that all you need to do is to check for this rate monotonic case. So the question then becomes, can I easily check whether if I give you a set of tasks and I ask you, can you run it on the processor to meet the deadlines? So what I've told you thus far is that you, under those circumstances that we have listed, independent tasks, deadline equal to period, the only thing I need to check is for the case when I assign priorities according to the order of the rates. But can I how do I check? Well, one way to check is for each one of the tasks, do that critical instant analysis. That is, I assume this task arrives together with a copy of every high priority task, and then kind of conceptually do a simulation to see whether it meets the deadline. Its response time is less than its deadline. So I can do kind of a pseudo polynomial time simulation of each one of the case. For each task, for its critical instant, I can do the simulation and make sure that things are working fine. But now imagine if an OS has to do it at runtime, every time you start a new task, it has to do all of this. That could be a little bit painful. So one of the questions has been, can I just look at the tasks and answer the question by solving an equation, whether it will meet the deadlines or not? What we saw previously is that it's not enough to look at the utilization. Like, we can't simply say that if the sum of what fraction of CPU each task is needing, if that's less than 100, then it is schedulable. That is not true. We already saw examples of it, right? Depending upon how we assign priority, even though the utilization was only 90%, one way of assigning priority will cause the deadline to be missed and the other would work. So it's not simply enough to say that sigma Ci divided by Ti, namely the fraction of the CPU, is less than 1. That's not sufficient. That's not a sufficient thing. So, could I given the C's and the T's, could I answer this? Could I answer this question? So it turns out you can easily construct examples that where even like 30% of the CPU may be idle and you are still not able to meet the deadline. And kind of intuitively, the idea is that if you are in this situation where a task arrives and this deadline is too close, then you are kind of in for trouble. So what we can say, and again, I'll if any of you are interested, come and talk to me about the underlying theory, but this kind of main thing is the following. What I can say is that if I give you n tasks and I look at what fraction of the CPU they are together using, so sigma Ci over Ti, if it is less than equal to this term, n times the nth root of 2 minus 1, then that task set is schedulable. And which basically means I can give them rate monotonic priority and it will work. Maybe some other priority ordering will also work, but at least rate monotonic will work. If the processor utilization is greater than this number, then it may or may not be schedulable, depends. And at that stage, you have to do that simulation type analysis to find out. Okay, so first quick and dirty test is this. Now, if you look at this number and take its limit n tending to infinity, you will find that it is basically ln2 0.69. So it basically says that if one lazy way of making sure that a set of tasks is schedulable is to pick a fast enough processor so that the utilization is no more than ln2, no more than 69%. This again, and you'll probably add some fudge margin and all. But this is basically saying that I'm kind of potentially using a CPU which is as much as 3/7, so whatever, 40% or so, 42% or so, too fast. Okay.
Where does the n to the 1/n come from?
Where does this come from? Yeah. So this is a little bit laborious analysis which follows, but you can start with a 2-task case, and you will see a pattern emerge in this thing. So I can point you to the paper. It's a pretty old paper which kind of shows this thing. But basically, the way it kind of works is intuitively that they start with saying that let's imagine I have a some ordering which works, but it is not rate monotonic. And then what they do is any time they have a pair of tasks which are out of order, they kind of swap it and nothing else will change, and they kind of go through that recursive analysis and eventually kind of end up with this formula. So so yeah, it's kind of a laborious paper to read, so you just have to trust me on this result. Okay. So give you a set of tasks, a processor which is 30% slower than 40% faster than what is minimum needed. Will always work, but that's probably not a very wise thing to do. It could be unnecessarily conservative. So what could we do? Well, so the thing is, so firstly, if I give you a processor, give you a set of tasks, you do this test. If it passes, you can say, okay, I'm done. If not, then you have to do that critical instant analysis. Okay, so now critical, or you could directly do the critical instant analysis, but remember that critical instant analysis requires you to effectively kind of do a simulation of sorts, which can be pretty slow. But how do we go around doing it? Yeah.
In critical instant, can't we just do for the highest priority?
No, you can't. So actually, it's a great question, and so you will find often. So firstly, you should say, can we not simply do it for the lowest priority task? So the point Vivek is making is the following. Let's say I give you 10 tasks, and let's say that test failed, right? Let's say the processor utilization came out to be more than 69%, or whatever, ln2. So now I'm basically saying you have to do the critical instant analysis. So his question is the following: can I simply look at the lowest priority task and show that it will not miss its deadline? Okay, so I will take that lowest priority task, do its critical instant, that is a copy of every highest priority task has also arrived, and then do a simulation and ensure that this instance of the lowest priority task still meets the deadline. Is it enough? Turns out not, because an intermediate task may miss its deadline still. Okay, so it depends upon the precise details in that case. So you literally do have to test for everyone. Okay, okay, so yeah, so this is kind of an example here, just numerically. I gave you some task. Is this schedulable? You check the U, okay, and in this case n equal to 3. So at n equal to 3, the threshold is 0.779. So instead of 69% is that, because we have 3 tasks. In this case, the utilization is 86%, so it's above the threshold for n equal to 3. So we can't say, we need to apply the critical instant theorem. Okay, so now to apply the critical instant theorem, what we can do the following. So firstly, we can see that task 1 and 2 together are schedulable because their utilization, you can check the summation of these two is actually less than the threshold for n equal to 2. Okay, so we already know that task 1 and 2 together are schedulable. We also know that in a rate monotonic assignment, task 1 will be the highest priority because it has the lowest period. Task 2 will have the next highest priority, and task 3 have the lowest priority. So we are so that much we know, and we know that 1 and 2 together are schedulable. So, but we added 3, and now we are ambiguous. So what we are going to do is all we need to do is to check whether task 3 is schedulable. And the way you can do a mental simulation is the following. You can say, okay, for me, so task 3 has arrived, and at the same time 1 and 2 have also arrived. But before 3 can even begin to run, the 1 and 2, the first copy that we got, they have to run. So we will take at least 50 time units before task 3 even begins to run. So at t equal to 50, task 3 begins to run, and it will keep running until 100, and at 100 another copy of task 1 will arrive, right? Because its period is 100. So at 100 the processor will get preempted, task 1 will run, and meanwhile I have run 50 units of this guy. So I have 18 remaining. So now at 100 this guy starts running, and it will keep running until 120 because it takes 20 time units. So at 120 the second copy of task 1 is finished, and now again the CPU comes back to 3, and it will start running, and at that point in time, so let's see, am I getting it right? Yeah, so it will start running at 120, and then it had 18 remaining, so it will finish at 138, and the next copy of a task would arrive at 145, so I'm okay. So I finished at 138, and which is less than the deadline which we had, and we are done. So in this case, we are okay. How much can I increase C3 before I run into trouble? 7 more, right? I mean, so I have a slack of 7 in this case. You can also use this kind of analysis to kind of figure out how much I can slow the CPU down before I run into trouble. Okay, so anyway, so anytime you see a slack, that's either an opportunity to use a slower algorithm, and a slower algorithm may have other benefits, like maybe it needs less memory, for example. Okay, or I can use a slower processor. Okay, so far so good. Is there a better test without doing that simulation? Now, this simulation wasn't too bad out here, but imagine lots of tasks and all, then it can take as much time as the product of the periods, basically. Okay, the hyper period. Much after the original paper in this space, around 15 years ago, so a better test came out, and this test, instead of simply using the ratio C over T, the sum of the C's, the total utilization, it makes use of the individual U sub I, individual Ci over Ti. And this one says that if U sub I plus 1, the product of that, is less than or equal to 2, then again the set of tasks is schedulable. So I give you a set of tasks. For each task you calculate the percentage processor it needs, that's the U sub I, and you do this computation, or a fraction processor it needs. So the fraction plus 1 product, if it is less than or equal to 2, it is again schedulable. And it turns out, I think in the example I had previously, if you were to apply this test, it would work. So this test is the best known test if you know the individual processor utilization. If all you know is the total processor utilization for the set of tasks, then the best known test was the previous one. If you know individual ones, then this is the best known test. And if this test fails, then you again have to do that analysis of the critical instant analysis. So how could I do the critical instant analysis? So I mean, I went through the mental simulation for you, but you could write it more systematically. So the way we could do it is the following. So let's say I am looking at I want to find the response time. So if I look at the highest priority task in the system, its response time would be its computation time, right? Whenever it arrives, there's nothing else to worry about. So whenever after computation time C, it would finish. So the response time of the highest priority task will always be equal to its worst case, its computation time. So that's straightforward. But if I look at an arbitrary task, something which is not the highest priority, then its response time is going to equal to its computation time plus an interference term. And this interference will depend upon all the other high priority tasks, right? By interference, I mean that they are going to use a CPU also. So I cannot get the CPU in a single stretch. So I have to worry about that I will get preempted and something else is going to eat up the CPU. So our job really now boils down to figuring out how much interference that exists. So how much interference is there? So let's say again I'm worried about task I. I'm trying to calculate its response time. And let's say there is some task J in the system whose priority is higher. Okay. Now let's assume that the response time of task I is R sub I. We don't know what it is. We are actually trying to compute it, but let's say it's R sub I. So now during this period R sub I, how many copies of task J will come? Well, task J has a period T sub J. So I will have ceiling Ri over Tj number of copies of task J to worry about, right? There's one right at the very beginning, so that's why we have the ceiling term. And each one of them have to finish because task J has higher priority. So task J is going to give me an interference of this much. Ri sub Tj ceiling, that's the number of copies of task J, times Cj, which each copy will take. And I have to play the same game for every high priority task in the system. So my total interference is going to be for every task in the set of tasks which is higher priority than I, so we are going to call it HPI, and number of copies times the corresponding thing. Okay, so we just take all these interference terms and we can say that's the interference that ith task will face. Is this clear to everyone, right? We're just looking at all the high priority tasks, the interference they will offer, we're just adding them up. And that results in a simple recursive equation. Response time of ith task is equal to computation time of the ith task plus the interference it will face, except interference is a function of Ri. So we have a fixed point equation of the form x equal to fx, and there is a non-linearity out here because of this ceiling term. So when faced with this thing, you solve it iteratively. There's a common approach. So you start with some assumption about R sub I. So a very reasonable assumption is R sub I equal to C sub I. Okay, it will be at least that much. And then you just iterate it. So that's what this thing is saying. You start with some estimate, W0, Wi0, and then you kind of iterate over this thing. One of two things will happen in this process. So firstly notice that here as I iterate, it can only go up, right? Because every term here is positive. So we are continually increasing. So one of two things will happen. Either we will converge, that is at some point I will find left and right side match and therefore have converged, or the right side will, I will end up where the current iteration value is more than the allowed deadline. So I have missed my deadline. So one of the two things will happen, right? We'll converge or we will exceed the deadline, and in either of these two scenarios, we can stop. So relatively straightforward algorithm, but the time it will take is equal to, in the worst case, kind of the product of all the periods, because we'll have to effectively kind of simulate for that long. So kind of straightforward conceptually, but just wanted to lay it out for you. There are other ways of formulating this thing also. It's not terribly deep, but and you can play all sort of games around this thing. You can answer questions like how much can I slow down the processor, or if I'm missing the deadline, then how much should I make the processor faster. I mentioned like we can begin to relax some assumptions we were making thus far. We were assuming that processor is running at a fixed clock frequency. I can maybe play games like change the frequency. So when a task which is at the I can increase the speed of the processor when I have a task with a tighter deadline, and I can slow it down at other times. So I can optimize for power. So there are all these games which these games around power and all are more recent, because power management wasn't a concern originally, but you can play all these kind of games. There's some pseudo code out here to kind of pull it off. Okay. One thing that we can so now what I'm going to do is I'm going to sort of mess with this model that we had thus far. So we made a lot of assumptions along the way. Tasks are independent, all these kind of things, and also we're going to relax one by one. One assumption we made was that period equal to the deadline. What if the deadline is shorter than the period? Okay, and the reason we might have deadline shorter than the period is because my period may be too long. If the period is, if let's say the sensor sample comes every second, then should I use the whole deadline of a second out here? That may not be acceptable for my end-to-end performance, right? Maybe if I'm using that sensor reading to shoot a weapon at an intruder, it would be too, the intruder would have moved, right? So my end-to-end deadline may be much tighter, and therefore I may have to use a tighter deadline at this processor. So oftentimes we have this situation where the deadline is less than the period. Of course, deadline has to be more than the computation time, otherwise we can't execute. So it turns out that the extension to this case is again very straightforward. I'm offering it without any proof at all. The extension simply is that you give priorities in order of the deadlines. Okay. Remember, this deadline is a relative deadline. What it is saying is, so let's look at this. Task 1, period of 20, computation time of 3, deadline of 5. It is basically saying a new instance of task 1 comes every time 20 time units, and whenever it comes, it has to finish within 5 time units after that. And it needs 3 units of computation time. So the generalization of rate monotonic is what's called as deadline monotonic, and it basically says that you should assign those static priorities in order of these relative deadlines. So in this particular case, if you notice, the periods were 20, 15, 10, and 20. So if I had gone by rate monotonic, I would have given the highest priority to task 3. But because we are doing deadline monotonic, and the way the deadlines are, the highest priority would be for task 1. Now, one very important caveat out here, that those theorems I gave, those formulas, geometric based on processor utilization, they are not valid for the situation where deadline is less than period. If you have deadlines less than period, then the only thing you can do is to do that critical instant analysis. Okay, you can still use that algorithm with some modifications so that you stop when you miss the deadline, but you cannot use those formulas that sigma utilization less than equal to that term based on n, or that type of. Those are only for the case where deadline was equal to period. So in this case, critical instant analysis is the only thing you can do. So we can handle this situation easily. So what I have not talked about is the case where deadline is more than the period, right? Now deadline more than the period immediately has other issues also, right? I mean, firstly, if deadline is more than the period, and if I actually always finish a task after its period, then I will have very soon an infinite buildup of the tasks. So clearly, on an average, I still have to finish less than the period, but maybe once in a while I'm allowed to exceed that. That would be the notion, and we'll see it, I think, a bit later on how to handle that. So the next slide set, which I'm going to start, but obviously not finish, is basically about relaxing some of these constraints and generalizing kind of the model to more interesting situations. What if I have a shared radio, for example? How do I deal with that? But main takeaway from this initial model, or sort of areas where we have some problems, is firstly, our whole model of priority is based entirely on deadlines. And remember, I had started out by saying intuitively when you think of priority, you might think of importance. And unfortunately, you can't ignore importance either. Okay, so now let's go back to our our model about deadlines, right? So now imagine, for whatever reason, the processor is undergoing some overload. Okay, so by overload I mean maybe because of a thermal emergency, the processor had to slow down. So in our timing based model, what will likely happen is that the tasks which are lower priority are the ones which are going to miss the deadline, right? Because they don't get the CPU as much. But the problem is that we were deciding high priority and low priority based entirely on the periods. Whereas when bad things are happening, when processor is slowed down, we might want to take importance into account. So I may have a very important task, but it has a low period, so it has a low priority. But when bad things are happening, I want its priority to be higher. I don't want it to miss the deadline. So this is basically saying I may have important tasks whose periods are long, and in a purely timing based model, they will miss the deadline. Can I avoid that? Another issue. So in this whole model, we kind of assumed that tasks are periodic. In fact, we assumed they are exactly periodic. The reality is a lot more complex because these tasks arrive because of an external process. A very common example is that it could be packets arriving from another computer over a network. So when the tasks arrive, they are not exactly periodic because of the delays. The source process, the one sender, may not exactly be periodic. There may be some jitter in it. So on an average, my audio samples may arrive every, let's say, 10 milliseconds, but it's on an average. If you were to plot it, there may be some jitter in it. So one way I can deal with this thing, well, so how can you deal with this thing? So if my incoming tasks are not exactly periodic, they have some jitter plus minus delta around the nominal period, how can you handle that situation? Put a buffer, right? Exactly. So I put a buffer to just basically add a constant worst case delay. So I kind of take the jitter into account. We put the size of the buffer would be equal to the maximum jitter. Excuse me. So if a task arrives too early, it will wait before it's picked up. So I can handle it that way. The only problem is I have now added a constant, if I don't do it properly, I've added a constant amount of delay in this process. So, but one has to take into account. What if I have tasks which are not periodic, sporadic, comes once in a while? Okay, so so you could think of it as this is a task. One way of thinking about it is a task which is periodic, but sometime it doesn't arrive, and if it doesn't arrive, I give the CPU to someone else. So I can handle it that way. Excuse me. Okay. More interesting, tasks that interact. So they use some common resource. So now we have a problem. So let's say there's a high priority task, and at some point it needs a radio. So it says, open the radio or whatever, write to the radio. But the problem is some low priority task may have already opened the radio. And a few lectures back, we had talked about mutex and semaphore and those kind of things. So the radio is locked by this low priority task. This high priority task is ready to run, but the resource is not free because the low priority task has grabbed the resource. And if you are really unfortunate, that low priority task may keep sitting there because other tasks of intermediate priority may keep bumping it off. So I can end up in this situation that this high priority task is waiting for a resource which is essentially locked by a low priority one. So intuitively, what would you do there?
So either disable like interrupts when there's a lock shot.
That doesn't work because you can't predict when the task, high priority task, is going to need the radio, right? So what has happened is, right now the high priority task wasn't running, so low priority task needed the radio, it grabbed the radio. Okay, except now the low priority task, before it finished with the radio, the high priority task arrived, and now it needs the radio. And meanwhile, there are a bunch of intermediate priority tasks which keep running, and so the low priority task is not able to run. So essentially, high priority task is waiting for the low priority task. Could you do something to get the low priority task?
You could change the priority of the
You could change the priority of the low priority task. Excellent. So basically, the intuition is that you can inherit the priority because by virtue of you are locking a resource which is needed by someone high priority. We'll see this, but again, this is the realization that this is an important issue didn't hit until there was one of these Mars Pathfinder mission, I think, which failed because of this. Okay, and after that, sort of that importance of this issue got realized. So this kind of transitive interaction between tasks are important. Tasks that interact. Tasks, like you were suggesting, tasks can lock out interrupts. So one cheap way of grabbing the CPU is forget all these mechanisms that the OS provide. You just disable the interrupt. If you disable the interrupt, timers are disabled, all sources of interrupts are disabled. Essentially, the OS is locked out. Okay, which is why you are usually, you will not be given control over the interrupts or disabling or enabling the interrupts. Okay, because you can literally stop the system. Tasks with deadlines greater than period. This creates its own set of challenges. And then I guess the more interesting stuff in recent years really has been when you are dealing with power together with time. So it's not simply your goal is not simply meet the deadlines, but meet the deadlines in the more energy efficient manner. And then finally, well, a couple of cases. So firstly, we have seen the emergence of processors with multiple cores. So I can actually have multiple tasks active in the CPU simultaneously because there are multiple cores. And the other one is dealing with end-to-end delays. So what happens in many systems is that it's not simply I have tasks coming in, I have to worry about deadline. What I have is I have a task coming in, gets processed on one processor, its output goes to another processor, its output goes to third processor, and then I'm worried about the end-to-end delay. And how do I split things between them? So I won't cover all the issues, but let's see some subset of these. Okay, so I guess in the remaining 4 or 5 minutes, I just want to talk about one of them. How do we deal with this issue that I may have some transient emergency situations? Okay, so this is a situation I have. I have a bunch of tasks, again given their periods and stuff like that. Except in this case, in addition to the worst case computation time, I've also given you the average case computation time. So I have worst case 20, but on average it only takes 10. Remember, I earlier said that the ratio between best case and worst case is often like factor of 10, 50. So I've given those times. And moreover, I have also added another one, criticality. So I have task 1, 2, 3, and 4, which are critical. That is, they should meet the deadlines, preferably, but 3 is non-critical. Now, looking at this model, what will happen is that if I were to assign rate monotonic priority, then I will assign priority in that order. 1 would have the highest priority, and 4 would have the lowest priority. When the let's say now imagine that there is an overload in the system, processor heated up, so it had to lower its frequency or something like that. Task 4 will miss its deadline, but in this model, I would have liked task 3 to miss its deadline. It is non-critical. Task 4 is more critical, so I would like the ordering to be the other way around. Except in this particular case, if you were to flip the order, if you were to give task 4 the highest priority, higher priority than task 3, then we miss the deadlines in the regular cases. So we want to be able to handle these situations more gracefully. This kind of a transient overload type situation. So what we would so we're kind of in this dilemma that at some times we would like to assign priorities according to importance, but our whole theoretical framework thus far is really based around timing, because we were trying to meet the deadlines in the normal case. So how could we approach this thing? So let's take simpler scenario. So I have 2 tasks. Computation times are 3.5 and 7. Periods are 10 and 14, and deadlines are 10 and 13. Okay, and the first one is not important, or less important, and the second one is critical. So looking at this, normally I would give task 1 the higher priority because its deadline is less than the deadline of the second one. Remember, we are in the deadline monotonic situation here, right? So task 2 will have lower priority, so now let's if I were to let's see. So if I were to could I make things such that task 2 is the one which meets its deadline? So the concept is the following. I'm going to divide the task 2 into 2 halves. So literally, I'll take the code, and remember, originally it was 7 time units long, C2. I'm going to divide it into 2 halves. Think of it like 2 function calls. I'll make function call 1, function call 2. And the way I'll do it is I'll say in every even iteration of task 2, I'll run function call 1, and in every odd instance of task 2, I'm going to run function call 2. So I've split the task into 2 halves. And now it's my original task, which was coming every 14 time units. I have a new task which comes every 7 time units, except in part 1, in even cycles, I do part 1, and odd cycles, I do part 2. So I've kind of manually split the task. And my deadline is now going to be remember, in one case I'm doing the part 1. In the case, the original deadline was 13. Now the new deadline is going to be 6 because I'm dealing because of that leftover 6. And it turns out that if this concept is called period transformation, so I have converted a slower task into a higher rate task. So basically, what I'm doing is I'm artificially boosting the priority of task 2 so that its rate is higher and its criticality would higher as well. So I kind of align criticality and rates together by doing this period transformation. But now the ugliness out here is this code splitting. Okay, that I had to take this code and split it into 2 halves. And the reason it's ugly is that what if that split point, that 50% point, was in the middle of a loop someplace, right? It's hard at it is if the code was just some sequential instructions, but now imagine I have some for loop and I have to split it into two halves. So from a purely software engineering perspective, it could be pretty messy to pull it off, but if I could, I have a way to kind of align, make the rate of critical tasks to be higher, so that my more critical tasks are also more higher priority. So I could play this game, and in fact, in the extreme case, I could do it many times. I could literally think of a task as sort of after every instruction. I could say I could think of if I have a task of 100 instructions, I could think of it as a task of 100 parts, and then really break it down into that granularities. But again, total nightmare. So I'm going to stop out here. I'm going to pick up this thread, but this issue of like how do we gracefully deal with these situations is something that we encounter a lot. So anyway, talk to you guys on Wednesday. If any of you want to talk to me about the project, come up to my office and I'll be there for a bit. Pardon me? Oh yeah, sorry. I'll do it.